a little bit about like how actually Cartan connections appear, like in three-dimensional gravity in a very natural way, and well, finally, like some work in progress. So, and future directions that, well, we've been working with my supervisor, Bernice Shores in Edinburgh. So, the only disclaimer is that, I mean, the work with my supervisor, it was about vortices, but in the Lorentzian setting, even though here today I'm going to tell like the Euclidean part of the story, because it's like, I mean, there are like some results, like precisely from the community working in vortices, and we can precisely like make the connections like better, like in this setting. But I will talk a little bit more, like at the end, like in these other directions. So then the first part about vortices. So the idea is precisely to see, I mean, I hope that at the end of this part of the talk, then you will be convinced that precisely Cartan connections is like a natural language, like to describe vortices. And well, I mean, as we saw like this morning, something that is like very important, like in the language of Cartan connections, is that we are working with Lie groups. And then for vortices, at least for the Euclidean part of the story, then we are going to work with these three. So then it's going to be SU2, it's going to be the special Euclidean group in 2 dimensions, and it's going to be SU11. And then there is, Schwarz, so my supervisor, and Catherine, one of his previous PhD students. They found like, let's say, some kind of like nice ways, like precisely to describe like all these groups that appear, for example, for vortices, and also, I mean, we will see. Well, I will talk a little bit about that also in the setting of 3D gravity, just like kind of like parameterizing them, so by a parameter. So the parameter is going to be lambda. So lambda minus 1 will precisely describe the SU2. Lambda 0 will correspond to the special Euclidean group, and then lambda 1 will be the SU11. And something nice, well, here we have like the Lie group, the Lie groups, but also, well, something nice about them is that they have like nice topologies, and precisely these topologies are the ones that are going to tell us, like,
sorry, what is H?
Sorry? H in the, here,
Yeah.
is going to be the hyperbolic.
Okay.
So, and yeah, so the topologies that we have, so then, well, for SU2 is going to be S3, for the special Euclidean group is going to be R2 times S1, and then for SU11 is going to be the hyperbolic plane, like space in 2 dimensions times S1. So then something that we can see is that, well, in these two cases, it's kind of like clear to see that precisely here, what we want to do in these two cases is kind of like to construct U1 bundles. Meanwhile, in this case, well, this one is also going to be like the U1 bundle, but instead of having like S2 times S1, we have the Hopf vibration. Okay? And something, I mean, and well, we denote like in a generic way, like these two groups by H, I mean, this mat BB and then the one corresponds like to the fact that we are kind of like normalizing, and then the lambda will tell us precisely in which of the three cases we are. And, well, precisely, I mean, so also something nice about these groups is that, well, we also have like a kind of like compact way to describe also the Lie algebras. So the Lie algebra is going to be generated by these three, so you can see clearly the dependence of lambda in the generators, and then the brackets, I mean, using just like simple like matrix multiplication and the standard commutator for the matrices, then we get that the commutation relations for this Lie algebra precisely, I mean, are written in this way. Okay, well, I'm using here the T plus and T minus, so using the standard fact that, well, T0 is going to be, I mean, that one, we are not like playing with that one, but T plus is going to be T1 plus T2, and T minus is going to be T1 minus T2. Yeah, kind of like the light cone coordinates, if you want to think in that way in the Lie algebra. So now, so here, so as I said, so something that we have here is that precisely, I mean, you can see that here what we have at the end, like topologically, is going to be like a Riemann surface times S1, and precisely we want to build up like U1 bundles precisely over Riemann surfaces. And actually, all the time when I mention Riemann surfaces, we are going to talk just about like three. I mean, there will be just like the three main players of all the talk will be, I mean, H2, R2, and S2, okay? And, well, we will see that this lambda precisely is going to tell us, well, I think you can now like guess it, but it's going to be precisely related with the curvature of the Riemann surface. So, precisely, so a little like comments about like the geometry of Riemann surfaces. So, Riemann surfaces with constant Gauss curvature, then the metric, I mean, using like local coordinates Z and Z bar, so the standard like complex conjugate coordinates, so we can write down the metric in this way. And then, well, you can kind of like take the square root of the metric, or if you want also like in the language of Cartan geometry, it's going to be like the coframe. So it's this E that is here. And then precisely the fact that this metric is, is going to give us a geometry that is with constant Gauss curvature is precisely encoded in two equations. And well, the first equation is called like the structure equation, and the second one is the Gauss equation. Okay, where this, well, E, as I said, so just like to introduce some terminology, so it's the coframe, and then gamma is going to be the spin connection. Okay, so a way to encode all the geometry of the Riemann surface with constant Gauss curvature then reduces to know that the coframe and the spin connection, they precisely satisfy these two conditions. Okay. And now, then something like nice is that actually we can just like combine these two equations in just one, and then we have like this proposition. So yeah, Ross is a previous PhD student of my supervisor, Callum Ross. So it's like the structure and the Gauss equations, the one that we saw before for the coframe and the spin connection. Then you can actually put them together. So in this H lambda 1 valued connection. So it's like with this specific form that precisely we are building up on this U1 bundle. So for that reason, we are precisely in the setting of Cartan geometry, where then we are dealing with a U1 bundle, and then we have like this connection that we are defining on the bundle is precisely not taking values in U1, it's no U1 valued, but it's actually, take values in the full Lie algebra, okay? And again, just remember that the lambda at the end is just like, all the cases are like, can be described exactly in the same way. And well, the proof is, let's say, quite easy. We just compute the curvature of this connection, then we get that this expression, and then the proposition is just telling us that the two equations that I showed you before just translates in the flatness of this connection, okay? So exactly what we have is that we can just like, so describing all the geometry of the Riemann surface, we can just put the coframe and the spin connection in this connection, and then the flatness of this connection is going to guarantee that precisely we have the structure and the Gauss conditions are satisfied. And now something also like nice, and is that this connection, let's say that it looks like I just took it out from the hat, then actually there is a nice geometrical interpretation of this one, and is that if we have actually this section map, so sigma is going to denote the Riemann surface, so this sigma precisely is going to depend on which lambda we're working. So for example, if lambda is 0, then it's going to be R2. And then we have like this map. So this map is just like a way in which it's a section of the U1 bundle over the Riemann surface to, And then, so if we use this map, so we have this one is a Lie group, we have our Maurer-Cartan connection there, and then if we pull back using this section, precisely we recover the connection that I showed you before. Okay, so it means that precisely this connection that we have here, we can recover it precisely as the pullback of the Maurer-Cartan form on H lambda 1, precisely using this section that is here. Okay, and well, here is just like this is like the parameterization that we are using. So I show you in the first slide like the Lie algebra. So well, it's like easy to see that precisely this is going to be precisely like the way to parameterize the elements in the group. Yeah? Just like exponentiating the Lie algebra generators.
But the H lambda is 2-dimensional. This was like a 4.
No, H lambda is 3-dimensional.
Okay, but still you had like 4 real parameters there. Right.
But there is, you still have the, this one precisely is like forcing the fact that, when you take like the determinant at the end needs to give you 1. Yeah, thank you. And now, well, so far we are just talking about like geometry, but well, I promise that we are going to talk about vortices and how we can use the language of Cartan geometry to describe them. So now, this is like the let's say like a kind of like mathematical description of a vortex. Of course, if you go like, I don't know, like fluid dynamics, and there are like another prescriptions, but this is kind of like the algebraic way to formulate them. And this is actually, well, it's not here like explicitly, but this is like the Manton definition, which actually he kind of like explored a lot of these geometrical approaches to vortices. So then for a vortex, we are going to have, when you talk about a vortex, you're going to have two real parameters. So it's going to be lambda 0 and lambda 1. It's not a coincidence that I'm using exactly the same lambdas as before, in the sense that, well, we have the lambda that it could be -1, 0, or 1. So precisely, we are going to have those like 9 combinations, yeah, for lambda 0 and lambda 1. So a vortex parameterized, or let's say labeled by these two numbers, so it's going to be a pair. So the pair is going to be, so the first part of the pair is going to be a connection, and the second is going to be a section of a line. So, well, a connection is going to be a connection like on the U1 bundle that we described before, where the Riemann surface. So in this case, the 0 corresponds precisely like to the Riemann surface that is like indexed by this, the one that is associated to the lambda 0. And phi is going to be a section of a complex line bundle. So it can be like, in this case, given that we are dealing with U1 bundles, so it's going to be like a section. And it needs to satisfy the so-called lambda 0 lambda vortex equations. So these are the equations, okay? So I'm not going into the details of these equations, but, well, I mean, they're like, they're also like so-called like in the language of vortices, there is something that is called the Bogomolny equation. So these are, I mean, I don't know if that makes sense to some of you, but these ones are like the Bogomolny equations. And, yeah, I'm not going into the details, but this is like the definition. And now, so this is like one of the striking results precisely in this like geometrical approach to vortices is the Manton. And then is that if we have a rational map that is going from our Riemann surface sigma to our Riemann surface sigma 0, so this one is the one that that is well, is actually is here. So we have that the Gauss curvature of sigma 0 then is going to be minus lambda 0, and the Gauss curvature of sigma is going to be lambda. Okay, so we are considering two Riemann surfaces with constant Gauss curvature. So then, if we take this map, this rational map, and then remember that to each of them we have like this. I mean, we have this geometrical way to like to encode the. Well, no, we have this coframe and spin connection that is a way to like encode their geometry. So precisely, we have that if we pull back the coframe, in this case is, yeah, in this case, sorry, here the 0 should be here, because actually we are pulling back something that is here. So if you pull back precisely the coframe of this surface, no, wait, yeah, sorry, the only thing is that, yeah, the 0 should not be here, but should be here, because you can see that precisely I'm pulling back the quantities that are without the 0 label. So actually, yeah, just like here, this is a mistake, the 0 should be here and not here, sorry. So then you pull back precisely the coframe on this Riemann surface, and then, well, that is going to give you, I mean, it's going to be precisely the coframe of the other one multiplied by this factor. And then you, I mean, you form this kind of like nice like connection, let's say, that is you pull back the spin connection of the sigma. Remember here it's not sigma 0, sigma. And then you take minus the spin connection of sigma 0. And then this, so the phi and the a that you obtain in this way, they precisely are going to be a solution of the vortex of the lambda 0 lambda equations. So again, the punchline here is that you take two Riemann surfaces, you have your map F, and then, well, this map, by definition, you are precisely defining the map between two Riemann surfaces with different like Gauss curvatures. So then you just like apply this recipe that is here, and then that is going to produce precisely solutions of the lambda 0 lambda vortex equations. Okay, and this is a result due to Manton. So precisely Manton like studied, if you check like the paper, what he does is that, so well, he proved this result, and then he started like to explore like precisely like different like kind of like he just considered rational maps as I am like stating here. And then what he does is like just like he goes case by case, and then he baptizes them in this way. So remember that minus lambda, so minus lambda 0 and minus lambda are going to be the Gauss curvatures, okay? So in this case, for example, you are taking rational maps between the hyperbolic space into dimensions and the hyperbolic space into dimensions. For example, here you are taking maps, I mean, the target space is going to be the hyperbolic space into dimensions, and the source space is going to be the true sphere. And I mean, another example is going to be, for example, this one, maybe. This one, that is going to be, so the target space is going to be the hyperbolic space in two dimensions, and the target space is going to be R, okay? And then, I mean, of course, we are considering these rational maps between these like Riemann surfaces, and there are like some kind of like constraints. But again, I mean, I invite you like for the details in Manton's paper, but just to say that he precisely studied these vortices and he baptized them integrable in the sense that, well, the problem we will see that is translated at the end in like again like a flatness condition for a connection, and then well, that kind of like is to guarantee that precisely we're dealing with integrable systems. And again, I mean, this is just like to show you that there is like a classification. This is like the standard terminology that the community uses. And well, this is precisely the result that I mentioned and why actually they are called integrable. So you have the map. Okay, so here is right. Yeah, here is from sigma 0 to sigma. And then, so you take, in this case it's an holomorphic, so actually this result was like extended. So for the Euclidean case, it was extended by my supervisor and Ross, Cartan. And for the Lorentzian setting, that's the result that we obtained like with my supervisor, and now with this, like, you can actually do it like in the Lorentzian and the Euclidean setting, and actually for holomorphic functions. Even though later I'm just going to show like some rational, like some examples will be precisely for rational functions. So you have an holomorphic map that is going from the Riemann surface sigma 0 to sigma, and then you are going to take this connection that is precisely a connection that is defined. So you can see that here we have sigma and E, but we don't have the 0, like 0 in subindex. So precisely these two are going to be the coframe and the spin connection of this Riemann surface. So then, if this is flat, so yeah, and so this is a flat H1 lambda value, so exactly as we considered before, then the flatness of the pullback is going to be precisely equivalent to the lambda 0 lambda vortex equations. So we know that this one, I mean, given that we are dealing with a Riemann surface of constant Gauss curvature, we know that this one is going to be flat. But now we take the pullback by, let's say, by the holomorphic map, and now the flatness of that connection is going to guarantee that precisely what we are getting, so this F at the end, is going to provide us with solutions of the lambda 0 lambda vortex equations. Okay, so you pull back, so the pullback is going to be this, and then well, you can see that precisely the quantities that are involved, that is this phi times E0, and this A plus lambda 0 are precisely the quantities that were involved in the expressions that I showed you before, and the flatness of this condition, of this equation, is going to guarantee that we are dealing with solutions of the vortex equations. And this is okay. And now, so just like to complete the picture, so all what we are describing here is like, well, I show you that actually this connection that we are like constructing in this U1 principal bundle over the Riemann surface, I show you that actually that one is coming from a pullback of the Maurer-Cartan connection on H. So now, like to complete the picture, there is also a definition. So this is like the definition of vortex that I presented before. It's a definition like at that level, but also there is a definition, again introduced by Manton, and it's now like the notion of like a vortex, but for the Lie group, okay? So not for like over Riemann surfaces, but for the Lie groups. So this is the definition, again is due to Manton. So now you have your Lie group, so it's going to be this one. We're just dealing with the three Lie groups that I presented at the beginning. So then a one form, so the vortex configuration as before is going to be two ingredients. So we are going to have a one form, that is we denote by A, and then we are going to have like phi, that is going to be like, it's going to play like the role of the phi that was like a section of this complex line bundle. So we have A that is going to be a one form on the Lie group, and then we are going to have a map that is going to be a complex function that is going, the target space is the Lie group, it's a complex value function on the Lie group. So then the pair is going to be baptized as a vortex configuration if we have this, if these equations are satisfied. Okay? And this tau is like when you write down the Maurer-Cartan form, this tau and tau bar are precisely going to be like, again, it's like in light cone coordinates. Well, when you expand the Maurer-Cartan, if you remember, we denote the generators of the Lie algebra by T0, T1, and T2, but then we like mix T1 and T2 to give us T plus and T minus. So then precisely this T is the one that is going to correspond to like the one form part associated to T plus, and then the T bar is going to be the part associated to T minus. Okay. So we are going to say that this pair is going to be a vortex, but now in the Lie group, so at the Lie group level, if we have that these two equations are satisfied. And you can see, well, the two equations actually, I mean, there is like a kind of like nice way, again, it's in the paper by Manton, where he explains why this kind of like is like the natural way to extend this notion of vortices on Riemann surfaces, but now to Lie groups, okay? But you can see that kind of like the expressions are very similar to the ones that I showed you before. And and now as I said, the idea is like to close the picture. You will see, I mean, just like there is a diagram at the end of this part of the talk where we are going to see actually how the different things that we have been talking about, they kind of like put together in this nice diagram. So yeah, sorry if maybe now they look like a little bit like disconnected results, but I'm sure that with the, I mean, let's say like with the punchline of this part, you will see how the different pieces kind of like fit together. So you have again, so you have a map that is holomorphic between the two Riemann, now it's two Riemann surfaces, because well at the end, even though now we are dealing with Lie groups, we know that these two we know that at the end all these Lie groups are actually like, I mean, we can build them as U1 bundles over a fixed Riemann surface, and that is kind of like also like the trick why Cartan connections appear like as a natural language to describe vortices. So you have an holomorphic function. Again, I mean, Manton proved it for rational, so then Ross extended to holomorphic in the Euclidean case. And then we consider, so this map, U, that is going to be a map that is going from the Lie group, like indexed by lambda 0, to the Lie group indexed by lambda. So the map is going to be given by this. And what we want is, so F is a map that is going from the Riemann surface 0 to the Riemann surface, like, the Riemann surface of Gauss curvature minus lambda 0 to the Riemann surface with Gauss curvature minus lambda. So now what we want to do is precisely, we want to lift this map from the Riemann surfaces now to the bundles. And this is exactly what we are doing here. So what we want, this U map, if you want to understand it in this way, is just like a lifting of this map from the base manifolds to the full U1 principal bundles. And so yeah, what you want is this needs to be a covering. And then what Ross proved, extending results from Manton, is that precisely, I mean, we are going to, and you can see that this is the analog of the Riemann surface case that I mentioned before. So is that we are going to have that actually, so a vortex configuration on this, or on the source Riemann Lie group is going to be precisely, we can obtain it in this way. So you can see that actually it's like very similar to the expressions that I show you for over the Riemann surface, like involving the coframe and the spin connection, but now it's like involving precisely the quantities that we mentioned before for the Lie groups. And well, these are some examples. So again, I mean, these are just like you can find this in Callum's paper, is that? But I mean, of course, I'm not going into the details, but it's just like to show you that given the F, actually there is like I mean, the formulas, let's say, for lifting the maps are well known, at least for the rational maps, for example, that are the ones that I'm presenting here. So for all the cases, so here lambda, remember that is the Gauss curvature of the target. Well, minus lambda is the Gauss curvature of the target. So all the cases that actually have lambda different from -1, then if you give me any holomorphic function, then you can always take a lift that is going to be given by this, and then you can check that actually, well, the previous theorem is actually telling you that actually if you take any f and then you use just like this f and this f2, then you can precisely get solutions of the vortex equations at the level of the Lie group. Okay? So this was in this table that I show you, like in the terminology of in the community of vortices. So now is when the target space is R2 and the source space is S2, the two-sphere. So you give me a rational map. So well, there are like some constraints, like to make the computation easier. That is, the degree of the denominator needs to be smaller than the one of the denominator. So you have these like explicit expressions for P and Q, and then the F's that you can take precisely to lift the map at the level of principal bundles are going to be given by these expressions that are. Okay? And the last, let's say, case, I mean, you can see that here I'm considering precisely the two cases, I mean, when lambda is precisely equal to -1. And then the last one, just like to complete all the picture and to have actually for all these 6 cases that I show you in the table. So now, again, you give me like a function that is going from H2 to S2. So then, the function, let's say, that could be written in this way. and then you can take like f1, then is given by this expression, and f2 is given by this expression. So again, I'm not going into the details because, well, at the end it's just like going like into the computations, but I mean, at the end, the purpose of the presentation is just like to show you this main idea that actually Cartan connection, I mean, like the relation with physics is also like in this branch of vortices. Yeah? That, I mean, I don't know how well known is that bit. And this is the picture that I promised. So, I mean, I hope that this picture is precisely going to, this is like a summary of all the things that I mentioned before. So we start, so if you remember, so the first part of what I was talking was at this level. So we were taking our U1 principal bundles over the Riemann surfaces, and then if you remember the information of the Riemann surface sigma, then we saw that it's encoded precisely in the flatness of this Cartan connection, because remember this one is a U1 bundle. I mean, what we are considering here is a U1 bundle, but this connection is precisely valued in all the full like Lie algebra of the Lie group. Okay, so for that reason, we are in the world of Cartan connections. Then we saw that precisely this map is holomorphic, and then we pull back, and then we have that the pullback connection satisfy also that is flat. Then we precisely recover these equations that are precisely the vortex equations. So this recipe here is telling us how we can actually get solutions of the vortex equations at the level of the Riemann surfaces. Now, we have the picture of the bundle, and then the second part was precisely how we lift this to the bundles. So then, well, this pi is just like the projection. I show you like for lambda equal to 0 and lambda equal to 1, then I mean it's clear like how is the projection, because actually these spaces are decomposed as the Riemann surface times S1. And for the case lambda equal to -1, then what we have is the Hopf vibration. So these sections, I mean, I described the two sections. So S, well, yeah, we described the section. And then precisely, we know, I explained to you that actually there is a geometrical connection of this, a geometrical relation of this connection, and it's precisely that it corresponds, I mean, like, if you take the Maurer-Cartan connection here and you pull it back via this section, and precisely you recover these flat connections. So now we are, I mean, the Maurer-Cartan form precisely is living now in the Lie group. Yeah, that is like if you want the full space in our U1 principal bundle. And now you have this F, and then you lift it, and now you apply like the same. So it's like almost like the analog here. So precisely, if we pull back this, then we know that precisely, I mean, when you pull back, what you are going to recover is precisely the equations of, let's say, the generalized vortex configuration equations, but now at the level of the Lie groups. Okay, and when this is like the full picture. So, well, I hope that this is like kind of like the part that kind of like you will keep in mind. So, and it's like, because, yeah, I mean, it's showing us precisely how, I mean, here we are like in the world of Riemann surfaces, here we are dealing with the geometry of Riemann surfaces. Meanwhile, here we are like at the level of Lie groups, okay? And this is telling us, so the bottom part is telling us how we can actually get lambda 0 lambda vortices, and this one is telling us how we can get lambda 0 vortex configurations, okay? And now the second, I mean, how much time do I have? When did we start? Was it like 10 minutes?
So you started a bit later, so you have still about 9 minutes.
Okay. So yeah, so as I said, so the idea is like, I mean, we are going. Mainly, the idea was to talk about like how we can use the Cartan connections to get solutions of the vortex equations. But now I'm going to mention something about the three-dimensional gravity that is actually kind of like what now we are like working with my supervisor. But well, what I'm going to present here is kind of like well known, like well for the community in 3D gravity. But again, I mean, I'm just going to show this in case that because even since like kind of like the original approach to 3D gravity, precisely like some ingredients of Cartan connections were used. Actually, we will see that precisely like the building blocks for spacetimes in 3 dimensions are precisely homogeneous spaces, and for that reason it makes like Cartan connections like the natural language to describe the theory. So some characteristics about the 3-dimensional general relativity. So the first thing is that, well, if you compute like for any 3-dimensional manifold, so if you compute the Weyl tensor, then it's going to be identically 0. So we are going to see the physical implications of this, but, well, I mean, the dynamical degrees of freedom of general relativity are precisely encoded in the Weil tensor. So for that reason, usually people say that three-dimensional gravity is topological, in the sense that you are not going to have precisely these degrees of freedom. So if your manifold is closed, actually, well, you're not going to have any degrees of freedom, and if it's like with boundary, precisely the degrees of freedom are going to be encoded in the boundary. And the second characteristic is that, well, you have the Einstein equations in 3 dimensions, and then they are going to reduce. I mean, you just like take the trace of this, and then this is showing us that precisely, I mean, as it was like the word was mentioned in the morning session. So all the solutions are going to be precisely Riemann, Einstein manifolds. So in all of them, the metric is going to be the Ricci tensor is going to be proportional to the metric, and precisely the quantity that is giving us the proportionality is precisely the cosmological constant. Yeah, I didn't mention it before, but this lambda is the cosmological constant. And these are the Einstein equations with cosmological constant. So precisely as I mentioned, so no degrees of freedom, so that is a consequence of the fact that Weil tensor is 0, is like trivially 0 in 3 dimensions. And the second is that precisely this equation is telling us that locally, I mean, this is outside sources, because sometimes people, I mean, let's say that if you are like in the setting of non-pure gravity, well, you like to include like point particles, and then outside these point particles that actually are going to generate like cone defects in the space-time, you are going to have that your space-time is going to be of locally constant curvature. And for that reason, so what we're going to have is that if you want to solve 3-dimensional gravity, and this is this is discussed like with some detail, let's say in the seminal paper by Witten from the '89. So the building blocks are going to be precisely the 3-dimensional manifolds of locally constant curvature, and then depending on the signature and depending on the cosmological constant, then you are going to have different like building blocks. So all the game for building space-times in 3 dimensions, then is going to be just like to glue together things like this, okay? And so here I can show you like kind of like which are going to be like the local isometric groups of the different like model space-times that you're going to have. So here you have the Euclidean group in 3 dimensions. Here you have Poincaré. Here you have well SL2, and here you have I mean this one is like a SO31, and this one is SO22. Okay, so these are the local isometric groups for these model space-times in 3 dimensions. And the nice thing is that actually all the possible building blocks are going to be precisely homogeneous spaces. So this, for that reason, I mean, also it makes of Cartan geometry like a natural like language to describe 3-dimensional gravity. And then here precisely you have, I mean, these are like the local isometric groups, and you can see that we can precisely recover all the model space-times precisely as quotients of these groups. Well, here sometimes I'm using like double covers by, well, in this case it's by the Lorentz group, and in this case it's by SO3. Okay. So these are the model spacetimes, and all of them are homogeneous. So if you want to reformulate this, and also like I hope that this is going to be kind of like to keep in mind, is that the building blocks for 3-dimensional gravity are homogeneous space. Okay, for that reason it's important like, to study the homogeneous space. And just a little bit of the physics, and to see actually how the Cartan connection appeared. So the theory, and this is like why actually Witten kind of like found out that 3-dimensional gravity is kind of like solvable in 3 dimensions, is because actually he managed to write down the Einstein-Hilbert action. Well, him and also simultaneously, who did that? Bañados and Zanelli, I think. Yeah, well, the people working in the BTZ black hole. So then they precisely managed like to write down to recover the Einstein-Hilbert action precisely from the Chern-Simons action. And the trick is quite, well, I mean, I will not say quite simple, because, well, it was actually like a striking like discovery. Actually, it's like a good way to mention why the theory is going to be topological. It's because, well, it reduces at some level like to Chern-Simons, even though the equivalence is a little bit subtle. So it's like precisely, I mean, remember that here what we have is M3, and then you are going to have your local isometric group. So M3 could be like any, for example, let's say that we reduce to one of our model spacetimes, and then we have our model spacetime, and then we have the corresponding like principal G bundle. So then what we need precisely in Chern-Simons, you are dealing with connections of this principal bundle. So these are not Cartan connections. But something that Witten actually did is that, well, he kind of like all these Lie algebras that I show you, all of them decompose in like a part that is kind of like rotations and boosts, and in a part that is like the translations, or like the ones corresponding to momentum. And then what he manages to split down precisely this connection in two pieces, and one piece is going to be like the field line or the coframe, and the other one is going to be the spin connection. Okay, so here a little bit, again, something that is, and for this reason, the two stories that I kind of like that I'm telling you here, they have this characteristic, and also, well, this is something why, let's say that my supervisor, he likes to work with this, and it's because the Lie algebras that appear and the Lie that appear, all of them, they have like a common way to be parameterized. So let's say that, of course, the details are different, of course, the geometries are different, the topology is different, but at the algebraic level, all of them can be parameterized exactly in the same way. The only difference can be precisely like encoded in a parameter. So in the previous case, in the vortices case, it was the Gauss curvature. In this case, it's going to be a combination of the signature. So this C2 is going to give us the signature. So when C2 is -1, we are going to be in the Euclidean. When C2 is positive, we are going to be in the Lorentzian. And lambda is the cosmological constant. And then I show you the local isometry groups. And the Lie algebra of all these local isometry groups could be written in this compact way. Okay? And precisely, well, these J and P are the ones that we use here precisely to decompose this connection on the principal bundle into a piece that is the field line and a piece that is the spin connection. And, well, this is just like an extra piece of information because, well, for Chern-Simons we also need like a bilinear invariant pairing in the level of the Lie algebra. And precisely, well, Witten found out that actually that space is two-dimensional, but if you want to recover the so-called like a standard 3D gravity, this is like the bilinear pairing that you need to use. There is another one, and these are the only two. I mean, any other, you just generate it as a linear combination of these two. And, well, yeah, just like finish. Yeah, sorry, I did extend 1 or 2 minutes. So, as I mentioned, so I restricted here like to present the Euclidean setting because we have this kind of like parallel story of Manton. But well, with my supervisor, precisely the idea was to generalize to the Lorentzian setting. And well, in the Lorentzian setting, as you can imagine, it's like you just like take the Lorentzian counterpart of the different things that we mentioned, like in the Euclidean setting. So instead of dealing with H2, R2, and S2, then now we go to the Euclidean counterparts. So it's the Sitter, the Sitter, and Minkowski in 2 dimensions. And this is something that we are like kind of like working now, like thinking also with Callum. And is that in 2001, Walton and Manton, precisely, they came out like with a generalization of now to non-abelian vortices. So instead of like dealing with U1 principal bundles, now well, you change U1 for something more general. And well, of course, in that case, well, like settings get more like involved. And about the 3D gravity, so again, I mentioned just like kind of like something that is very well known, but the idea is the punchline of that part is that Cartan connections also appear like in a natural way in 3 dimensions of 3-dimensional gravity. And then the first part is actually how to deal using the Cartan terminology with the insertion of particles. So, I mean, the Chern-Simons like counterpart of the story, you just like include them and you just like put them. You take like puncture Riemann surfaces, and then you just like fix like the autonomy like of the connection. You fix it like to a specific conjugacy class. So now we are kind of like it's very similar like, to the Chern-Simons part of the story. And the second is like Capriotti. I mean, this year he released like a paper where he's like dealing with a fine 3D gravity. But actually, I mean, this is like the main like the idea. So here you have this part that is how you see Lorentz inside Poincaré. So he just like extend precisely to the affine version. So using this kind of like compact way to parameterize all the local isometry groups that appear in 3D gravity, then you can actually do like exactly the same, but not just for, I mean, he did it like specifically like for this case, and well, this is just like a kind of like an extension of this particular construction that he made. And well, this is all. Thank you, and yeah, if you have any questions, please ask, and also in the tutorial.
We don't have much. Thanks for the lecture. We don't have much time for questions. Just one quick.
Can you make just a quick connection between the formulation you described, the vortices, and like how we might think of them in fluid flow? Is there some?
I was expecting that question because actually when I was doing the presentation, I was like, if I put a picture of a vortex, people will ask me like, okay, how can you read off like the Cartan connection, the Cartan connection associated with the vortex? So yeah, in that case, actually yeah, I mean for me, kind of like when I think about vortices, honestly, I think like more like at the I mean, you have like a, kind of like a functional that you can define, like to describe like the theory if you want, like at the Hamiltonian level. And then the equations of motion are precisely the two equations that I showed you as the vortex. But yeah, if you ask me like, well, I think like solving these equations and then you kind of like plot something specific, you can recover like the profile probably of the.
Thanks. Katharina, the last one.
Yeah, just one question. Is this at all related to the theory of Higgs bundles? These vortices equation?
I mean, I don't know how to. I will say maybe. I mean, actually, well, this phi that probably for that reason you're asking, because this phi is precisely the Higgs potential. Exactly. So honestly, I'm not familiar with the Higgs bundle. So with Higgs bundle, so I mean, I prefer not to say maybe something that is wrong, but could be. I mean, I'm not sure. Yeah, honestly, prefer not to say.
Yeah. So thanks.
Thank you.
So let's